Hello, 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 everybody. This is Mr. Folly. And welcome to hitting another huge chunk of this worksheet for kinetics and Big Idea 5. So you got to complete this table below. So notice here, this is the linear one, A versus T. Okay, so this has A versus T, so that's going to be zero order. How do you know? Linear, A versus T. This one right here, this is still A versus time. Okay, so what I guess we got to do here, what must be plotted on the y-axis to give a straight line? That is going to be, if it's zero order, you have to do the concentration of A. Okay, so for this one, what I have to do is actually bust out a calculator and make some ordered pairs here. So let's see, 4, 3, 2, 1. So this is going to be 1 comma, what is that, 0.18. Then I'm going to have, what is that, 1, 2, 2.5 comma, 2.5 comma, 0.16. And then I have this right here, which is 5 comma, 5 comma, see, that's 0.05. So let's see here, 6, 7, 8. Yes, this is it. 0.05, 0.06, 7, 8, 9, 10, 11, 12. 5 comma 0.12. And then I'm going to have 10, 9, 8, 8 comma, let's see here, 6, 7, 8, 9.5. And then what we're on 8. So then we have 10 comma, let's see here. So that's going to be 6, 7, 7.2. And then what I'm going to do is I'm going to graph those. So when I graph those, I'm going to see what happens. No, I'm not going to graph that. What I'm going to graph is, so it's going to be ln versus t. So I'm going to do the natural log of 1, and then natural log of 2.5, natural log of 5, natural log of 8, and so on and so on. So I'm going to pause that and throw that in there and tell you what I get. On this side over here, in that way we know it's going to be either 0, so we know already it's not 0. So it's either going to be 1 or 2. So when I do natural log will tell me if it's first. Okay, so I'm going to pause it and okay, so what I did was I graphed time. So I've got time and natural log of A. And when I graph this, I get an equation that looks pretty much like a straight line. The R squared value, we're going to do this in our lab, is 0.998. Then I graphed 1 over A versus T. And you see how this one looks more curvy. It's not quite as straight. And the R squared value for that is less. So that means that that first one is, no, I forgot. ln A versus T. And ln A versus T is first order. How do you know? So that's weird. It's writing very weird. Maybe I'll try it. So it's going to be first order. And how do you know? You know because ln A versus T is linear. Okay. And then what you're going to do, you saw how I did it in Excel. I thought you'd be able to see it. Same thing for this one. We know this is, we know this is not 0 because it's not linear. And we know that this is going to be second order because 1 over A versus T is linear. So what I did again, and you can put this in your calculator, you can see where I plotted the points. I did catch that. I called those 0.95 and it should have been 0.095 when I put them in there. 0.095 and 0.072, I think is what it was. But you graph them. So you graph A versus T, 1 over A versus T, and ln A versus T. So that's how you can tell. What plot must be plotted to give on the y-axis to give a straight line? So I'm looking at first order. I'm going to get rid of my not zero so I don't think of that again. First order is ln A versus T. And this one is A versus T. And this is 1 over A versus T. So you can tell that's actually, these two are kind of pretty much the same. What is the order of the reaction with respect to NO2 if the data from the lab plotted as shown in the graphs below? Explain. So this right here tells us that 1 over A versus T is in there. So it's second order because algebraically a second order reaction is linear with 1 over NO2 versus T. Is that 102 or 102 negative? Just NO2. Okay. What is the order of the respect to N2O5 if the data from the last plot is shown in the graphs below? Explain your reasoning. So this is my linear one. Oops. This is my linear one. So on this one, this right here, well, all of them, these are all the same. This is the same data point. It is first order because algebraically a plot of ln A versus T is linear for first order. Data from the lab is plotted below. Determine the order of the reaction with respect to A. Explain your reasoning. Ooh, I'm going to connect the dots. Not linear. Not linear. Linear. So 1 over A versus T is second order. Second order because algebraically a second order reaction is linear when 1 over A versus T is plotted. Complete the table using the AP Chemistry Equations Constant Sheet. So, I lost my little bracket thing there. So the equation sheet part we're looking at is right here, the kinetics part. And as I said before, this first part is the zero order. The first one is 0, then first, then second. So let's take a look at it. So the integrated rate law for 0 order is AT minus A naught equals negative KT. AT minus A naught equals negative KT. And remember, these are in brackets, meaning it's in concentration. And then first one, just to show you where it comes from, ln A minus ln A naught equals negative KT again. And then this one is 1 over AT minus 1 over A naught equals positive KT. So again, I think I forgot to put my brackets around it. Yep. So, and then the half-life is T1 half. The only one you have to know is 0.693. So it's ln2 over K. Okay. Determine the rate constant or the half-life of the following first-order reaction. Half-life is 36 seconds. So that means 36, I'm using this equation right here, equals 0.693 over K. K equals, calculators assemble, 0.693 divided by 36, and I get 0.01925. The rate constant of this. So these are first order again. So the rate constant, so T1 half equals 0.693 over 2e negative 2. And 0.693 divided by 2e negative 2. Oops, I hit negative 3. Negative 2 is 34.65 seconds. So this says seconds -1. So that's where that's going to come from. And I suppose if I put units on here, this would be seconds -1 too. K is 25 seconds -1, so T1/2 equals 0.693 over 25. Weird thing about natural logging something is if you natural log it, the unit goes away. There was some proof I saw sometime on how that's true. I'm going to ask you to believe me on it. That'll do it. All right. Put the seconds back as it rolled away. Your answers to 30B and 30C discuss rescue and half-life and rate constant. Oops, those ones right below before. Oh, 39A and 39C. As the rate constant increases in magnitude, does the half-life increase, decrease, or remain the same? The half-life, oh wait, as the rate constant increases, decreases. So if we look at this, so we've got 0.0195, so I'm going to do a little table, K and half-life. So when K is 0.019, the half-life is 36. When K is 0.02, T1/2 is 34. When K is 25, 0.02. So notice as K, going this way, as K went up, T half-life went down. Well, so K up and half-life down. There you go. And that was straight on the notes too for it. Refer to the data table above. The half-life of a reaction was measured under various conditions. So let's see here. Here's the half-life. The half-life of the reaction trial 4 is less than trial 1. Explain why in terms of activation energy. So trial 1. So let's see what we have different here. Half-life is the same. Initial cis-2-butene. It's the same reaction. In this one, the initial amounts changed, but it doesn't really matter much. Temperature went up, and the half-life went down. So explain why in terms of activation energy. So a higher temperature means more particles have the energy to react, so they react faster. And the half-life, if it reacts faster, goes down. A certain reaction is first order. Determine the amount of time required for the reactant to go from 0.5 to 0.25 if the rate constant is that. So first order, we're looking at ln(AT) minus ln(A0) equals -KT. So determine the amount of time, which is what I'm looking for. So I'm going to do the natural log. Amount of time t is the second one. ln of 0.25 minus ln of 0.5 equals -K, 1200 t. So let's see here. Natural log of 0.25, enter, minus quantity natural log of 0.5, enter. So I have, that's half-life, duh. So I have -0.693 equals -1200 t. T equals, divided by -1200, 5.78 e -4. Well, that's not very long. 78 e -4 seconds. Okay. There you go. So remember, the bigger, we had this up here. A bigger K means a smaller half-life. So this is a pretty big K. It's a pretty small half-life. Determine the order for each reaction in the data table below. Explain your answer. Okay, so the other way to do this, and I like this table one, is I look to see what the change is. So I notice that these are all a constant change of 15 seconds. So as I go down here, it's 75. Here is 37. That means it's not linear. So this is not A. This went down by 0.7. This went down by 0.7. This went down by 0.7. That is the same change, so that is linear. So ln versus t, this guy right here, because ln versus t is first order. Okay. Reaction 2. This went down by 86. This went down by 43, 47. Not linear. This went down by 0.35. This went down by 0.26. And yeah, that's not the same. So this went up by 0.0015. This went up by 0.0015. So up by 0.0015. So this is the 1 over b. So this is second order. And why? The why for that is because a constant change. Constant change is linear. So here we go right here. This one changes by 12.25, changes by 12.25, changes by 12.25. So this is 0 because the constant change is linear. Complete the table below for the half-life if the reaction is first order. Assume the half-life is 15 seconds. The half-life is percent of parent nuclear percentage decayed, 50. Number of half-lives, 1. Elapsed time, 15 seconds. Percentage remaining, percentage decayed is 75. Number of half-lives, 2. Elapsed time is 30 seconds. Again, so every time I'm dividing by 2. So percentage left is 87.5. Number of half-lives is 3, 45 seconds. This is 93.75. Half-lives 4, and it's 60 seconds. A certain reactant is second order. Determine the final concentration if the initial concentration is 0.45 molar and 15 seconds have passed. The rate constant is blah, 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 blah. So it's second order. Second order is the 1 over AT minus 1 over A naught equals positive KT. That's from the equation sheet. So the final concentration is what I'm solving for, 1 over AT, minus the initial concentration is 0.45, 1 over 0.45, equals K, 1.24, E negative 2, times T, 15. I'm just going to make sure that my units jive, and they do, seconds and seconds. So we do the right-hand side, 1.24, E negative 2 times 15. So 1 over AT minus 1 over 0.45 equals 0.186. So I'm going to add 1 over 0.5, 1 over AT is going to equal, so 0.186 plus quantity, 1 divided by 0.45 is going to be 2.40, 2.41. So then to solve for AT is going to be 1 over 2.41, which is going to be 1 divided by a second. Answer, 0.415 molar. Okay. Determine the beginning concentration of a 0th order reaction. If the concentration after 25 seconds is 0.5 and the rate constant is so 0th order is AT minus A naught equals negative KT. So the amount at times T is 0.5, so it's going to be 0.5 minus A naught equals negative 1E negative 3 times T, 25 seconds. So A naught, I'll do negative A naught, I suppose. Negative 1E negative 3 times 25 minus 0.5. And then I guess I'll make it positive. I can do this in my head. 0.525 molar. Possible reaction mechanism for the conversion of ozone to O2 is shown below. What is the molecularity of each step? So 1 is unimolecular, 2 is bimolecular. What is the overall equation? O's will cancel. And I'm going to have 2O3 yields 3O2. Notice how it does balance. These are the things on the product side. Reactant side. What is the intermediate in the interaction? O. It forms and then is used up. Nitrous oxide is believed to decompose in two-step reactions. Slow, fast. Write the equation for the overall reaction. Got something to cancel there. Okay, so 2N2O, 1, 2. So don't have any reactants left. Oops, not plus. Yields 2N2 plus O2. Okay, I'll write the rate law for the reaction. So I'm looking at just rate law is always rate equals K times the slowest step. N2O, there's only one of them to the first. Which step has a higher activation energy? The highest activation energy slows it down. That is the rate determining step. So that would mean step uno. Consider the reaction mechanism below: fast, equilibrium, and slow. Nobody cares about the equilibrium. They tell us that all the time. It doesn't matter. Determine the rate law for the reaction using the steady state approximation. Okay, so again, I told you if it says steady state approximation, nobody cares about those words. You just figure out what it would be. So this is my slow state step, but notice I've got an intermediate. So I got to pull the other ones in there. So rate equals K, no squared, times bromine. That's it. Another mechanism for the conversion of ozone shows the possible destruction of the atmosphere by no, as shown below. No. What is the overall equation? Let's see. Canceling. Oops. So O3 plus O yields 2O2. Notice how here's my dividing line. O3, O, O2. What is the intermediate in the equation? No, 2. What is the role of nitrogen monoxide in the equation? Explain your reason. It is a catalyst. It is a reactant that reforms. What is the molecularity of each reaction? Both of them are 2. Not 2, that's not the molecularity. The molecularity is bimolecular for both. What is the rate law? So slow step, look at those coefficients. Remember, rate law always starts with rate equals K times O3. Now, you do include the catalyst because it's impacting the rate. Okay, even though it's a catalyst, even though it's not in the overall reaction, it's O3 times the concentration of no. Isn't that interesting? 51, experiments were conducted to study the rate of the reaction represented by the equation below. Initial concentrations and rates of the reaction are given below. Determine the order for each reactant from the data given your reasoning. Okay, so this is times 2. This is times 2. So rate equals K, no, times H2. So I just found out that H2 changes the same, so it's first order. And then here we go, times 2. And here we go, times 4. So no squared, H2 to the first. Determine the order for each reactant, I guess, NO2 second, and then H2 is first. Calculate the value for each constant K, include units. So my rate is 1.8 E negative 4 equals K times no squared, 0.006 squared, and H2 0.001. So 1.8 E negative 4 divided by 0.006 squared divided by 0.001. I think this would be a big number. It's not, 5,000. K equals 5,000. And then canceling out, so I got 3 molarities, becomes 2. molarity to the -2 seconds to the -1. Following sequence of elementary steps is a proposed mechanism for the reaction. Based on the data presented, which is rate determining? So this is my rate law. This is my rate law. So that means I need to have a step that will include both of those. Step 1 has the NO squared, but it doesn't have the H2. This one has the H2, and see how that pulls it down? So it is the step 2, because H2 is in the rate law, and the intermediate required, the NOs to form. So the mechanism is consistent with the observed rate law and the overall stoichiometry of the reaction. So slow step produces the rate law. And then I just got to see what cancels out. N2O2 cancels. H2 doesn't. N2O2 cancels. H2 doesn't. N2, H2O. So then my overall reaction is 2 no's plus 2 H2s. 2 no's plus 2 H2s yields N2 plus 2 H2Os. N2 plus 2 H2Os. So summing steps matches the balanced equation. All right, 52. Almost there. Hypothetical reaction has the stoichiometry 2x plus y yields z. The following initial rate data was obtained. All the measurements made at the same temperature. So I'm sure it's going to say give the rate law. Rate equals. All right, so rate equals K, X, Y. I'm feeling like a man. Get it? It's a chromosome joke. When this doubles, when X doubles, the rate doubles. Same, that's 1. Let's see here. Here. When Y doubles, X doubles. Same, Y1. Calculate the rate constant. So let's do the first one. 7e -4 equals K times 0.2 times 0.2. K equals, and it's a bad looking K on my part, 7e -4 divided by 0.2 divided by 0.2 is 0.0175. And that's going to be molarity to the -1 seconds to the -1. Okay, look a little better. I don't know that I succeeded in that, but there's my answer. The reaction is carried out with K is 0.8 and Y is 0.6. Determine the rate of the reaction. So again, I'm going to just plug it in. Rate equals K, 0.0175 times 0.8 to the first, 0.6 to the first, equals 0.0175 times 0.8 times 0.6 is 0.0084. And that's going to be in molarity. Hey, we're in minutes this time. I called that seconds. How dare I? How dare I? A student claims you can determine Z after 20 minutes by using the reaction rate determined in the 1C. Explain why the student is wrong. You can determine Z after 20 minutes by using the rate determined in C. Explain why the student is wrong. The rate determined the Z. What's Z? Okay, the rate of Z after 20 minutes by using the rate determined in 52C. This is instantaneous rate. Okay, so here's my thought process. I think you might be able to do this. So if I were to do X, so I know X is first order. I could do, and these are first order, so I could do ln xt minus ln, I don't know why I did A. Ln xt minus ln x naught equals negative kt. So I have time, I have k. All I need, I want to find out this. This is what I'm solving for. Explain what student is wrong. We don't know initial concentrations. Initial concentrations. If we did, what we can do is if I did x, right? So if I found that x value, so let's say that I found, I don't know what that rate is. Hypothetical chemical reaction stoichiometry is this. It's got to tell me what that rate is in molar per minute. We don't know the initial concentrations, and rate isn't labeled. I guess actually we don't even need that. So if I did that, if I had the initial concentration, I could find the amount at time t, and then my rate, oh, it's instantaneous rate. Oh, yeah, you're stuck. That's fine. We don't know the initial concentration, the rate isn't labeled. Select the mechanisms below, the one most consistent with the observed data. Explain your reasoning for each mechanism. So this one, the slow step, this is yes. Matches rate law. And it is 2x plus y yields z. So matches rate law. I'm going to put stoich and rate law because it balances. 2x's plus y yields z. This slow step, no match rate law. Well, I'm almost done. Okay, I'm going to pause and come back to you later. All right, I'm tetrified? No, I'm not tetrified. I am terrified right now that I'm this far into it, finishing up with a long break in the middle of teaching a class or two. You heard the bell and see how it goes. This is my slow step. If this was my slow step, then my rate law would be rate equals ky, and that does not match. So no match rate law. And then identifying intermediates or catalysts and their action mechanisms above. So we can move these so I can highlight them. Okay, so I will start with catalysts. So I will start with catalysts. So my catalysts are things that are reactants that reform. So X doesn't reform, Y doesn't reform, X, Y, and those don't reform. X doesn't reform, right? And Y doesn't reform. Y doesn't reform. M is so a catalyst has to be a reactant. Nope. So an intermediate, I'm going to change my color. Intermediate, that didn't change my color. At least it didn't to me. It probably did to you. My intermediates are something that forms and gets reused. That's M. Something that forms and gets reused. M. Something that forms and gets reused. M. Something that forms and gets reused. N. So on that spot, we don't have any reactants that reformed again, so that's it. And that, maybe I got to do 53. I'll do that on the next one. So that'll be it. This is long enough, that's for sure. And I will say toodles. Thanks for hanging on through the whole thing, or part of it. No.